In this video, I am going to outline how to solve non-homogeneous second-order differential equations. Here, I make some assumptions. The assumptions are that P, Q, and T, these coefficient functions here, and the right-hand side non-homogeneous part, they are continuous function on the interval under consideration. Okay, so this is a non-homogeneous differential equation with P, Q, and G to be continuous functions. Now, to solve this, we kind of take a sort of very simple yet very powerful approach. Okay, so let's make this assumption that you have two solutions. Okay, two solutions, y1 and y2. These are two solutions to this differential equation which is non-homogeneous. This y1 and y2 are solutions to the non-homogeneous differential equation. Now, if that is the case, you can plug in these values into this equation and the right hand side and left hand side should be equal, right? It should satisfy it in other words. So it's going to be y1 double prime plus p of t times y1 prime plus q of t times y1 is equal to g of t. Similarly for y2, so I forgot the one here. Similarly for y2 is going to be y2 double prime plus p of t times y2 prime plus q of t times y2, no prime here, y2 is equal to g of t. Now, at this point, what I'm going to do, I'm going to go ahead and subtract the bottom equation from the top equation. Then I'm going to get y1 double prime minus y2 double prime. However, I can write it as y1 minus y2 double prime because the properties of derivative allows me to do that, right? Plus p of t. Similarly, I could write y1 minus y2 prime plus q of t times y1 minus y2. And that must be equal to nothing but 0 because g of t minus g of t is going to be 0. All right, now if you look at this equation closely, this one, you discovered something in a way. Look, this is nothing but a new solution to the corresponding homogeneous part. So if g of t were to be 0, then y1 minus y2 is going to be a solution to the homogeneous part of the equation. That's very interesting. So we just found a solution which is just the difference of two solutions to this non-homogeneous differential equation, and their difference is actually a solution to the corresponding homogeneous equation. So that tells me that I could write it as y1 minus y2 is equal to c1 times y1. c1 is some arbitrary constant and y1 is one of the fundamental solutions, and similarly c2 times y2, and c2 is an arbitrary constant or some constant rather. y2 is the fundamental solution, and y1 and y2 are linearly independent. So we just took the difference of two solutions to this non-homogeneous differential equation, and that difference turns out to be a solution to the corresponding homogeneous differential equation. Now I can rewrite this thing as y1, okay, is equal to c1 y1 plus c2 y2. Then I can add y2 to it on the right hand side. Now, if you look at this equation, that's kind of interesting. This is the homogeneous part, okay, which typically we call it y sub h, and this is the non-homogeneous part, or which is some solution which you call y sub p, or particular solution. So this y1 is just some solution, right? So in general, we could say that y, the general solution to this non-homogeneous differential equation, is going to be y sub h, the corresponding homogeneous differential equation's solution, plus some particular solution to the non-homogeneous equation. And in real world, typically, we will have to kind of find this particular solution. And for that, as it turns out, when your g of t is something of the form like a times e to the power rt. This is one combination. G of t is equal to a times cosine of bt plus c times sine of dt. Okay, a, b, c, and d are constants. This format, or some polynomial g of t is equal to some polynomial. Okay, then it becomes easier. Okay, it becomes easier to find the particular solution. And as it turns out that these special functions, these are very useful functions, polynomials, trig functions, and exponential functions. And for this important set of or classes of functions, you can many times find the g of t, solution for the non-homogeneous portion. That means you find the particular solution. And then homogeneous part is easier to find, and you put them together to get the general solution. And that is how, by the way, you will be solving non-homogeneous differential equation. And this method, by the way, is called the method of undetermined coefficients. Okay, method of undetermined coefficients. But I just wanted to give you a general outline of how to solve non-homogeneous second order differential equation using the method of undetermined coefficients. Now, if this doesn't work, if you cannot guess the particular solution, then there is another way of approaching the problem, and there would be a topic for another video. I hope that this discussion was helpful. Thank you very much.